All right, regulation of glomerular filtration rate, your GFR. Now, we need to be able to regulate the kidneys because there's a lot of things going on with the kidneys. So we have basically 3 different ways that we regulate our kidneys. The first one is going to be basically renal autoregulation, so the kidney does it itself. So the way that the kidneys auto-regulate themselves, the first one is going to be called myogenic contraction. So myogenic contraction, myo means muscle, genic means the beginning, contraction. So when we talk about myogenic contraction, we're going to be talking about contraction of the smooth muscles in the afferent and efferent arteriole. I have a lot to discuss on that. Now, the next thing is going to be your tubular. So when we say renal tubule, you're talking about your proximal convoluted tubule, glomerular feedback. We'll discuss this in detail. Now, this is also going to cause changes within the smooth muscles of the afferent and efferent arteriole, and that's why we say renal autoregulation. Now, one big difference between these is when you say myogenic contraction, this is going to be if you have a change in blood pressure, so the arterioles are going to stretch, so changes in blood pressure is going to regulate this. But when you say tubular glomerular feedback levels, this is going to be based on the changes in amounts of sodium and chloride, which is table salt. So when you have changes of sodium chloride, when you get dehydrated, or when you have a lot of fluid in your body, your sodium chloride levels in your blood are going to change, which is going to trigger changes with your GFR. Now, the second one is neural regulation. Neural regulation, we're mostly going to talk about the sympathetic nervous system. In the sympathetic nervous system, we're going to say that's fight or flight. Most of the time when you're running, when you're scared from maybe a clown chasing you, you shouldn't stop and have to urinate. So sympathetic nervous system is called fight or flight, and we're going to talk about what's going on with the renal corpuscle during times of neural regulation. And then the third one is going to be hormonal regulation. So for hormonal regulation, we really need to review the renin, angiotensin, aldosterone system, the RAAS, and then the next one is going to be atrial natriuretic peptide, which is the hormone produced in the heart. And then the third one is antidiuretic hormone, which is stored in the posterior pituitary. So, hormones, the renin, angiotensin, aldosterone system, you definitely need to review that. Atrial natriuretic pressure, you need peptide, you need to review that, and antidiuretic hormone. So, we will review those as we go. Now, before I talk about GFR, the first thing I want to talk about is your myogenic contraction. So, first of all, you have to remember that when you discuss your blood vessels, especially arteries have a pretty thick layer of smooth muscle that goes in the center of the artery or arteriole. Now, myogenic contraction, a lot of the ways that we control our GFR is going to come from the smooth muscles control, or the smooth muscle contraction inside of arterioles. So when we talk about smooth muscles and arterioles, this is the lumen. This is where blood is going to pass. So basically it's open. This is going to contract. when we say that it contracts, that is called vasoconstriction. So basically your lumen size gets really small because your muscle is contracting. That is vasoconstriction. Now, how much fluid can enter from your faucet, if your faucet is an arterial, if you contract your smooth muscle? So you decrease the size of the lumen. So this would be called vaso for blood vessel constriction. So obviously, if you have vasoconstriction, you decrease the blood flow because you have constriction. Now, if you increase the diameter of the lumen, which sometimes happens, and we are going to see things happening with our arterioles of the renal corpuscle, the lumen size gets really big. So you still have smooth muscle, but the smooth muscle is literally going to relax. So we call this vasodilation. And when you have vasodilation in any blood vessels, you have increased blood flow because the lumen size is a lot bigger. So we're going to be discussing a lot of changes within the afferent and efferent arteriole, which is part of the renal corpuscle. So we often describe these things in terms of a sink. So this would be the sink. Now the faucet is the afferent arteriole. This is where water enters into your sink, and then the drain is how it exits. So if you think of these in terms of a faucet and a drain, the afferent arteriole can vasoconstrict and it can vasodilate. So you can figure out what's happening with your GFR based on the afferent arteriole. So I'm going to come back to this picture. So literally, your afferent arteriole, which is going to approach, can vasoconstrict and it can vasodilate. So we're talking about GFRs, glomerular filtration rate, how much filtrate is produced if you vasoconstrict the afferent arteriole or if you vasodilate the afferent arteriole. But because we have the efferent arteriole, you can also do the same thing. So efferent arteriole is where it exits, where filtrate, the fluid exits. So this one can also vasoconstrict. It can also vasodilate. Now, when you vasoconstrict and vasodilate, you have changes in your GFR. So for me, I always think of these in terms of this is the faucet and this is the drain. So if we looked at the afferent and efferent arteriole, we are creating filtrate. The amount of filtrate is going to be determined based on the amount of fluid that can actually get to the glomerulus. So if you vasoconstrict, you decrease blood flow to the glomerulus if it's on the afferent side. If you vasodilate, then you increase blood flow. So we have two arterioles. So we are discussing the GFR. I want to know the glomerular filtration rate, not by numbers, when we change the shape and diameter of the afferent arteriole and efferent arteriole. So your GFR is going to increase or it will decrease based on the size of the diameter. So you think of this in terms of the faucet and the drain and how much filtrate is actually going to be produced and fill up the sink, how much filtrate is being produced based on the size of the blood vessels. So first one is your afferent arterial. So we can always, label these. Efferent arterial is going to exit. All right, so if we vasoconstrict the afferent arterial, does your GFR go up or down? So you're cutting off blood flow to the glomerulus. If you cut off blood flow, then your GFR will go down. So when it vasoconstricts the afferent arterial, you would say you have a decreased glomerular filtration rate. However, if your afferent arterial dilates, then more fluid enters into the glomerulus, so this would increase your GFR. So the whole types of regulation that we're going to talk about is going to basically be it either vasoconstricts the afferent arterial or vasodilates, or vasoconstricts the efferent or vasodilates. So you need to get your head around this first. Now, efferent. Efferent is going to drain, but your efferent arterial can also vasoconstrict and vasodilate. So as the blood exits the efferent, if it vasoconstricts, the drain is closing off, then obviously it's going to keep more filtrate inside of the renal corpuscle. So this actually is the opposite. You increase your glomerular filtration rate because you're closing off or constricting the efferent arterial. But if you vasodilate it, if you dilate the drain, then more fluid is going to be able to exit. But you have to remember there's 3 types of pressures. You have your filtration rate, you also have blood colloid osmotic pressure. You're always going to have something that exits, but the amount that can exit is going to be based on the efferent arterial. If it's dilated, obviously that's going to decrease your glomerular filtration rate because it's going to be draining the sink faster than you can actually produce filtrate or urine.